This is Jack Jackson. We're going to be going over the solutions to the problems that I introduced in the previous video on applications of integrals. This is some review over this quick unit on applying integrals that we do in Calculus 1 or possibly in Survey of Calculus. More advanced applications or just additional applications of integration will be covered in a later unit. So number one of the most basic things we can do for integrals is do areas. So here we have the curve y equals 5x, which is this green line right here, and y equals 17x minus 2x squared, which is this blue parabola. And we can see what the graphs of those look like right there. And you could just kind of, even just looking at it, it looks like they cross at 0, 0 and at 6, 30. But we can kind of find that algebraically like this by finding the simultaneous solution there by substituting 5x and place the y in the second equation there, solving for x. So we add 2x squared to both sides and subtract 17x from both sides. We get 2x squared minus 12x equals 0. We can factor out a 2x and left with x minus 6. So that's equal to 0 when either the x is 0 or the x minus 6 is 0, which says x is 6. So sure enough, that's correct. Plug them back into, well, just the first one is the easiest. 5 times 0 is 0. 6 times 5 is 30. But if you plug them in the second one, you also get 0 for when x is 0 and 30 when x is 6. So we see those two points of intersection, and what we're wanting is that area that I've got shaded here kind of in red in between. I did this in GeoGebra. It tells me the answer should be 72. Let's see if we can verify that. So what we're doing is we're integrating top curve minus bottom curve over that interval. So that's 17x minus 2x squared is the top curve in that region, and 5x is the bottom one. We're going to go from 0 to 6. So subtracting there, we get 12x minus 2x squared. Finding an antiderivative is easy. This is continuous on that interval, so we can use the fundamental theorem of calculus. Power goes up 1 to 2, divided by the new power. 12 divided by 2 is 6. That power goes up to 3, divided by 3, that's negative 2/3 x cubed. Evaluate that expression from 0 to 6, so it's parentheses minus parentheses. First parentheses is this function with the top number put in, 6, minus, and then the second parentheses has this function with the bottom number put in. I'll just do right to left. That's 0. That term's also 0. 6 cubed times 2 divided by 3 turns out to be 144. It's negative because of that. 6 squared is 36 times 6 is 216. Add those together, you get 72. And you can also do that if you have a calculator available. Even a TI-84 will give you an exact correct answer on that, because it will Simpson's rule works perfectly for cubics and actually fourth degree polynomials and less. It'll work perfectly for well, actually third degree polynomials and less. So it'll work perfectly for a quadratic like that. So there we go. Areas. Another thing we can do is find an average value of a function. Now this one we have to build a function. So since they told us population of a certain region is growing at a constant relative rate of 4% per year, its current population is 861,752 people. What's the average population over the next 15 years? Round to the nearest person. P is the population, T is the time since now in years. Okay, since it is growing at a constant percentage rate, that makes it exponential. The base is 1 plus the rate when that's a relative rate. This is not an exponential rate. So that base is 1.04. And so we have 1.04 to the t times that initial amount here. Notice when you plug in t as 0, that goes to 1. That's our starting point. And every time we're multiplying, each time we go up by 1 year, we're multiplying by 1.04. That's going to keep our original amount plus add another 4%. So that's our formula for our population. That's given by this green graph here. Okay, and I've got it graphed from, well, from 0 to 15 and just a little beyond that. Now, if we want to find the average value of a function over an interval, we integrate it over that interval, and then we multiply by 1 over the length of the interval. Well, the width of the interval there is 15 minus 0 is 15, so we have a 1/15th times the integral from 0 to 15 of our function. I went ahead and brought that coefficient out front, so that's 861,752 over 15 times the integral from 0 to 15 of 1.04 to the t. Exponential function, its antiderivative is the same function, and then divide by the natural log of the base there. So now we have a natural log of 1.04 in the denominator out here. And I evaluate from 0 to 15. We can factor all this out front. So it's just 1.04 to the 15th minus 1.04 to the 0. 1.04 to the 0 is, of course, just 1. And then at that point, there's an exact value, but we would want to approximate that because it's all an approximation anyway. And so plug that in a calculator, which I did right up here. You can't see the whole thing, but that's what I did. And it turns out to be about 1,173,215 to the nearest person. And if I do that in the calculator, it also gives me the same answer. The way you can visualize that is this integral is the red area that's beneath the curve over that interval and above the x-axis. And it's the same area as this blue area under this rectangle, where the height of the rectangle is this value. So if you look at those numbers, you've really zoomed in a lot. So those are pretty big numbers there, but that's the 1.1 million, 1.173 million right there. So that's the average value of that function. Let's see here. This should be a t. Okay, so the velocity of a particle moving along the x-axis is described by v of t equals 12 minus 3t cubed. The particle starts at the origin at time 0. Give exact and approximate answers. Note the distances are all positive always. What's the total distance the particle moves from time 0 to time 20? So one thing is interesting to note is 12 minus 3x squared is, when is it equal to 0? Well, it's when 3x squared equals 12, x cubed is 12, x cubed is 4, so x is a cube root of 4. So you notice that actually when x is less than the cube root of 4, that this is in fact a positive velocity. We're going to the right, but then we're going in the positive x direction. But then when we get past the cube root of 4, which happens, cube root of 4 is not very big, so it happens pretty quickly. Then from there on, we're turned around and going back the other direction. So it's going in the positive direction for a little bit and the negative direction for a little bit, but you want to add those together. And so what that turns out to be is the total distance is the integral of the absolute value. Now to integrate this absolute value, we need to break it at this point here because the absolute value is a piecewise defined function. So we want to go from 0 to cube root of 4 and then from cube root of 4 to 20. Then this one, the first one, is positive so that we can drop the absolute value. The second one is negative under the absolute value, so we get the opposite of that, which is why we have a negative out front. In either case, the antiderivative is just 12x minus 3/4 x to the 4th, but then we evaluate it like this. So this is the cube root of 4 goes in here and here, minus, then 0 goes in both places, minus, and then down over here we evaluate this one, plug in 20, minus, and then plug in the cube root of 4. Okay, so you got just a little arithmetic to wash out here. So this first term is there. This one is here. Let's see. If you take 3 of these powers, we'll just give you a 4 here, cancel that 4. So you're left with the minus 3 and the other cube root of 4 there. Okay, that's 0, that's 0. 12 times 20 is negative 200, and the negative here makes it negative 240. That negative makes a negative here. That's a negative there. Yeah, that is a negative. That's a negative, but so is that. So those two negatives make a positive here. Fix that, come on. So that's a positive, and that works out to be 120,000. You can do that in a calculator if you want. Well, you could do it by hand, but it's 120,000. Okay, that negative and that negative make a positive here. And negative, 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 3 negatives makes a negative here. And again, 3 of those cube root of 4s makes a 4, cancels that. So we have that. So let's see what we've got here. These double up. So that's 24 of the cube roots there, and then minus 6 cube roots of 4. That's 18 cube root of 4. And 120,000 minus 240 is that, 119,760. And if we approximate that, that's approximately, that's the exact value up there, right? And approximately 119,789. If we did it in our calculator, here's the exact value then worked out as approximate decimal, and here's the definite integral here worked out approximately with the calculator, and we get that agrees, those agree with each other, and that gives us our value. Now that one is how do you visualize that? Well, here's the function, and here's a zoomed in portion of some of it. It starts out up here, has positive for a while, then at the cube root of 4 becomes 0, then it goes down negative. Somewhere around here it turns around, or it actually just keeps on going down. But we're going from here to here. So it's actually the green area plus the red area is the total distance traveled. Zooming out where you can see all the red area, you can't really see the green area very much. It looks like this. Okay. Now, the net distance the particle travels is the absolute value of the integral. Now this time we don't have to worry about the absolute value to the end, so it doesn't affect our integral. Once again, the antiderivative is 12x minus 3x to the fourth. We go from 0 to 20, which is worked out here. These two are 0. Again, that's 120,000. That should be a minus there, so that's correct. But it should be here. Yeah, that should be a negative because of this. But that's negative there. That's positive 0 and 0. So that's a negative 199,760. Well, so that says that would be the red area, the green area minus the red area. But then you want to take, so it says that we ended up 199,760 units to the left of where we started, wherever that was. But this says that the net distance, of course, is the absolute value of that. It's a positive 119,760. So that's how far away from our starting point we ended up. This is the total amount of time we traveled. So we traveled to the right a little bit, then we went back to the left a lot. So the first one is the green area plus the red area. The integral is the green area minus the red area, and the second answer here is the absolute value of that, which turns out to be the red area minus the green one. All right, another big important area that we can look at for functions and doing antiderivatives and integrals is probability. So the probability density function for the duration of calls within a city is given by P of x equals 0.6 e to the negative 0.6x. where x represents the duration in minutes of a randomly selected call, what percentage of calls last between 1 and 4 minutes? Well, that's just the integral of that between 1 and 4. If you integrate from 1 to infinity, from 0 to infinity, this should be 100%. So the area under the curve from all the times that matter, which are really from 0 to infinity, that area should be 1. You could check, I'll leave it to you to check that out, that it is. But the probability we're looking for is this green area right here, which is just the integral. So let u be negative 0.6x, du is negative 0.6 dx. You put a negative 0.6 here, divide by negative 0.6 out front, so that makes that a negative 1. And then we get e to the u for our antiderivative. Then we want to evaluate from 1 to 4, so we put a 4 in here and a 1 in here and work this out. So this is, so I went ahead and distributed the minus. The two minuses make the plus, so I put this term first, e to the negative 0.6 minus e to the negative 2.4. That's exactly, approximately is this to lots of decimal places, or in percentages, about 45.8%. All right, the next one is a business application. We do a lot of these in survey of calculus. Suppose that supply and demand for a product are given by P equals 288 minus 4x minus x squared, and P equals 160 plus 4x plus x squared. So we want to draw the graphs. So that's easy enough. First of all, these are first quadrant graphs. X represents, let's see, P is the product, is the price. That's the dollars per item, the unit price, which has to be positive. And X is the number of items, which also has to be positive, maybe 0. So you're looking at a first quadrant only graph. So even though the formulas might suggest there's more to the graphs, only the first quadrant makes sense. And really, it only makes sense, you know, like up to where this touches the axis. So something like this would be a reasonable window to graph this on. Now, the one that's decreasing should be the demand function, and that is, let's see, that was the, let's see, the decreasing one is this one right here, 288 minus stuff. So it starts at 288 and comes down. That's the demand. And how do we know that? Well, we know that as we increase the price, the supplier is willing to supply fewer items. So that's a decreasing function. Whether you're thinking of whichever one of these you're thinking of as the independent variable, which is the dependent, it doesn't really matter. It's you increase one, you decrease the other. So that's demand. And then supply is going to be an increasing function. So that one starts at 160 and then adds stuff to it. So it's going up. Okay, that the demand curve represents the behavior of the consumers, okay, the buyers. So as the price increases, they're less likely to buy. Whereas the supply curve represents the behavior of the suppliers or producers. As the price increases, they're more likely to supply. So that's an increasing function for supply, decreasing for demand. Okay, so anyway, we got that. The market equilibrium is where the two cross. You can actually work that out exactly, not too bad, by putting these two equal to each other and solving. It's a quadratic equation thing, so we can use a quadratic formula. The negative 2 minus 2 squared root of 17 turns out to be a negative number, which is off of our screen. It's not reasonable for the context of the application. But the negative 2 plus 2 squared root of 17 is approximately 6.25. That is the x value of this. And on my calculator, I would probably work this out and store this. Or if I have my calculator available, I might just do a calc intersect, calculate the intersection of these curves, and we see that it's 224 for y and about 6.25 for x. Okay, and it actually works out exactly 224, as you can see here if you work out the details. Now we want the producer surplus. The amount of money that actually changes hands is this $224 per item times the 6.25 items is the amount of money that changes hands at the equilibrium point. But the producers would have been able to, some of the producers would have been willing to supply at a lower price. So this blue area represents the savings from the producers' perspective above what they would have been willing to the willing to provide the product. So had everybody been willing to provide it at the least amount, had everybody paid exactly the amount that they would be willing to supply, the lowest they'd be willing to supply it for, we would have gotten the area under this curve here, down here. But instead, we actually get an area up here. Areas on this graph are dollars, right? So this blue part is the bargain from the standpoint of the supplier. So that's what's called the producer's surplus. And so the function we're integrating is the top curve minus the bottom curve. The top curve is 224 minus the bottom one is the supply curve, which is this one right here, 160 plus 4x plus x squared. And we go from 0 up to that mark of equilibrium. I just did it on the calculator, which is going to do as good as you can possibly do anyway, and even though it's not a hard one to do by hand. And to the nearest penny, I get $240.49. The consumer surplus would be above this line and below the purple curve. It would be in this area up here. A certain bond is guaranteed to pay $250 plus 32 T dollars per year for 15 years, where T is the number of years from the present. So each year, this bond is paying off a little bit more, and it's doing it as a continuous flow of money. And assume the money can be invested at an interest rate of 4.5% compounded continuously, which is today's rates. That's a pretty good return on your investment. But find the total value of the income stream. So if we just see how much money is going to actually come in, what we're doing is integrating that function from 0 to 15 times dt. So for some small time increment times this would approximate the income over a short period of time. Add those up, take a limit, we've got an integral. Okay, so that's 250t plus 16t squared for our antiderivative. Evaluate from 0 to 15. It's done like this. These two at the end are 0. 250 times 15 is 3,750. 16 times 15 squared is 3,600. Add all that together, you get $7,350. And so that's the amount of money that this thing will eventually pay out. Slower at first, more later on. And of course that would, if you graph this line, that would also be the area of that shape underneath. Probably a right trapezoid would be the area underneath. That would be the area. Would give us that. So this is if you want to do the present value of it, the idea is take the money and as you put it in, as soon as it comes in, instead of spending it, let it accrue and let it grow by investing it until the end of the 15 years and then see what you got. That's the future value. And then the idea, well, what would be an amount I could just take and invest, a lump sum I could take today and invest and get that same amount of money at the end. That would be the present value. And the way you figure that is you take the flow rate times e to the negative interest rate times t dt and integrate that. And to do this one requires integration by parts, which we certainly could do. But a technology solution is fine for a number, so we're just going to use a technology solution here. And so we integrate from 0 to 15 there, that function. And you see here, this is a TI-84 screen. And that's $5,052.45. So it's actually going to pay $7,350 out gradually over time, a little bit less at first, a little bit more later on. But if you were to take a $5,052.45 today and invest it and cash it in at the end of 15 years, that would be the same thing as taking the money as it comes in and invest it and then cash it in 15 years. Okay? And I believe that's the last one that we have here. So hopefully that gives you a little taste of some of the things that we can do with integrals. Now we're going to have a whole other unit in Calculus 2 where we talk about things that we can do with integrals as well. But these are some that we cover in, at least I cover in Cal 1 and in Survey of Calculus.